It's March 14, 1945. On a cold morning in Lincolnshire, England, a single Avro Lancaster rumbles down the runway. The aircraft sits so low on its landing gear that the ground crew exchange nervous looks. The weight pressing on those tires seems impossible to bear. Inside its bomb bay lies a monster 22,000 pounds of hardened steel, packed with Torpex explosive, a weapon heavier than some entire fighter planes. Squadron leader C.C. Calder at the controls understands exactly what he's flying. His Lancaster carries more destructive power than 5 American B-17 flying fortresses combined. And that's not a boast. It's physics. It's engineering. It's the fundamental difference between how Britain and America fought the air war over Europe. The Lancaster wasn't just another bomber. It lived in its own league. A machine built for sheer payload, for bending the rules of what a single aircraft could do. Across the Atlantic, American crews measured success by volume. How many bombs, how wide an area they could cover. A B-17G, the mainstay of 1945, could haul about 8,000 pounds on a short trip. But stretch that mission deep into Germany, and it dropped closer to 4,000 or 6,000 pounds to save enough fuel to come home. So 5 fortresses together could manage roughly 20,000 to 30,000 pounds of explosives. But that math misses one crucial point. Those bombs would scatter over miles, drop from different altitudes, at different moments, across separate impact zones. The Lancaster, on the other hand, could unleash all 22,000 pounds on a single mark. One aircraft, one bomb, one precise strike. That kind of focus changed the nature of the war from the air. Some targets simply shrugged off traditional bombing runs. Submarine pens sealed beneath 23 feet of reinforced concrete. Rail viaducts built by 19th century engineers to outlast generations. And vast underground factories carved straight into mountains. Thousands of smaller bombs couldn't touch them. You could fill the sky with explosions and still leave those structures standing. The Lancaster was built to end that stalemate. It wasn't meant to do what 5 B-17s could. It was built to achieve what 5 B-17s never could, even in theory. It carried the kind of weapon that didn't just rewrite the rulebook on bombing, it burned the old one entirely. By March 1945, that Lancaster was carrying the Grand Slam, a bomb so vast its inventor, Barnes Wallis, had sketched the idea years before war broke out, but hadn't dared hope anyone could ever lift it. The Lancaster changed that. Suddenly the impossible had a way into the sky, and the last months of the European war were quietly transformed in ways histories often downplay. Wallis didn't begin with a bomb and work backwards. He began with a problem. Working at Vickers Armstrong in 1939, he obsessed over a question few engineers were asking. How do you destroy something built to take direct hits? His solution was ruthless in its clarity. Rather than smash at a target's surface and hope the structure failed, attack what holds it up, the ground underneath. He called it the earthquake bomb. The idea flipped bombing on its head. Drop a very heavy, very streamlined bomb from extreme altitude, ideally around 40,000 feet, and let gravity and aerodynamics turn it into a supersonic spear. It wouldn't detonate on contact. Instead, it would slice through soil and rock, burying itself tens of meters underground before going off. The blast would radiate through the earth like a miniature quake. Foundations would crack, piers would tilt, and buildings designed to shrug off surface blasts would collapse from below because no one had planned for that angle of attack. Wallis's notebooks read like a mix of seismology, mining know-how, and ballistics. The weapon had to be enormous, far beyond anything in service, with a long, hardened casing to survive the violent impact, and packed with Torpex, a naval explosive already proven to be far more powerful than TNT. By 1941, his specs were fixed: 22,000 pounds, roughly 26 feet long, and no existing bomber could carry it. The Air Ministry didn't dismiss his math. They simply put the project on ice. At that time, Allied bombs rarely weighed more than a couple of thousand pounds, and even the new 4-engine heavies, the Short Stirling and the Handley Page Halifax among them, were only just reaching operational maturity. Wallis's earthquake idea was brilliant on paper, but at first unworkable in the real world. So he scaled it down and gave birth to the tall boy. Still huge for 1942, at about 12,000 pounds, but suddenly doable if the right plane was adapted. When the tall boy entered service in June 1944, it validated everything Wallis had argued. One bomb, dropped on the Somme railway tunnel in France, drove down through 60 feet of earth and rock before going off. The blast collapsed the tunnel and stopped a German panzer division that had been racing toward Normandy. That success forced the Air Ministry to sit up and take notice. If a 12,000-pound weapon could do that, what might a 22,000-pound monster achieve? By the end of 1944, the pieces finally fell into place. The Lancaster existed in numbers, and industry could build the bomb. The Grand Slam shifted from theoretical marvel to living, terrifying weapon. This isn't to say the B-17 Flying Fortress was flawed. Far from it. It was a triumph of American design thinking, optimized for a specific job: daylight precision bombing from high altitude. Boeing's team in the late 1930s designed the Fortress to fly above most flak, aim using Norden bomb sights, and survive enemy fighters with sheer defensive firepower. 1350 caliber Brownings guarding the airframe. Every decision reinforced that mission, but that mission also set hard limits. The B-17's bomb bay was about 11 feet long and just over 3 feet across at its widest, split in two by a central structural beam, carrying huge loads between wings and fuselage. That beam wasn't a mistake you could simply remove. It was the spine that held the airplane together through violent maneuvers and hard landings. The Fortress was perfectly suited to racks of 500 and 1,000-pound bombs released in patterns, not to swallowing a single enormous 22,000-pound bomb. Its strengths were real. Its role was different, and geometry and structure, not bravery, set the limit. It put a hard limit on what a B-17 could ever carry. Internally, the biggest single bomb the Fortress could swallow was about 2,000 pounds, and even that meant tearing out bomb racks to make room. Then there's the raw weight math. A B-17G's maximum takeoff weight sat around 65,500 pounds, with an empty weight near 36,500 pounds. That left roughly 29,000 pounds for everything else: fuel, crew, ammunition, and the bombs themselves. On a long-range run into Germany, you couldn't skimp on fuel. A typical deep penetration mission needed on the order of 2,800 gallons of fuel, roughly 16,800 pounds. That eats most of the available payload. Add 10 crew members with their life support gear, oxygen bottles, and the ammunition for 1350 caliber guns, and suddenly the B-17's theoretical 8,000 pounds of bombs exists only on paper. In practice, for missions to Berlin and beyond, most fortresses carried nearer 4,000 to 6,000 pounds of explosives. Any more, and you risked not coming home. The U.S. approach treated that not as a handicap but as an advantage. American doctrine leaned into numbers, massed formations, hundreds of planes, thousands of smaller bombs raining down to saturate an area. The logic was statistical. You don't need one perfect hit if 300 aircraft can blanket an industrial district with 1,200 tons of explosives. That method demolished open-area targets like cities, rail yards, and dispersed factories. But it failed where concentration and depth were required. Submarine pens with reinforced concrete roofs, massive viaducts, and subterranean factories didn't care for swarms of smaller bombs. They needed a single concentrated punch that burrowed deep and released all its force in one place. The B-17 simply could not be turned into that kind of delivery system. The Grand Slam was 26 feet long, more than twice the B-17's internal bay length, and it weighed nearly 3 times the Fortress's realistic bomb capacity on long missions. You couldn't stretch its structure or its bay geometry without breaking the airplane's fundamental design. The Lancaster, by contrast, was the product of a different gamble. In 1940, Avro's Roy Chadwick and his team set out to build a 4-engine heavy, where the top priority was bomb load and flexibility. Defensive guns, crew creature comforts, and even range were secondary to one question: how much could this airplane carry, and where could it put that weight? The result was radical. The Lancaster's internal bomb bay ran about 33 feet uninterrupted, a single, clear trunk from well forward of the wings to far aft, designed to swallow the very large, oddly shaped weapons that other bombers simply couldn't accommodate. No heavy internal beam divided its belly, just one giant unobstructed cavern, ready to swallow bombs the rest of the world thought too big to drop from the sky. In standard trim, a Lancaster could carry about 14,000 pounds of ordnance, already more than a B-17's theoretical best. But Chadwick and his team had planned for more. They built the bomb bay so its doors could be swapped for bulged fairings that dropped below the fuselage, turning the bay into a lightened cavern. With that modification, a Lancaster could accept weapons up to 33 feet long and hold weights that seemed to defy aerodynamics. Pulling that off took extraordinary structure and clever load paths. The Lancaster's airframe used long, massive longerons and a distributed attachment for the wings, so stresses spread across many points instead of sitting on one central beam. That layout tolerated off-balance loads and violent shifts in the center of gravity that would have snapped other bombers in half. Hang a 22,000-pound Grand Slam under the rear fuselage, and the Lancaster sagged. Its landing gear squatted. The tail dipped, but the frame took the strain because it had been designed for unusual loads from the start. Power was the rest of the equation. 4 Rolls-Royce Merlin engines, roughly 1,180 horsepower each, combined to make about 5,120 HP, enough to heave a fully laden Lancaster toward a 72,000-pound maximum takeoff. With a Grand Slam aboard, many Lancasters were operating at or above 70,000 pounds, right at the ragged edge of what engines and structure could survive. Takeoff runs lengthened, climb dropped to around 200 feet per minute, and handling became sluggish. But the airplane left the ground, and that was the point. To make the missions possible, crews and engineers accepted hard compromises. The mid-upper turret was removed to save weight and reduce drag. Armor plating was stripped. Some sorties carried less fuel and therefore less range. Those trade-offs ran counter to American doctrine, which prized crew protection and endurance. But Britain in 1945 was willing to accept risk for unique effect. The result? A capability no other Allied plane could match. A single aircraft delivering unprecedented destructive power to one precise spot. By March 1945, fewer than 30 Lancasters had been specially altered to carry the Grand Slam. They flew for 617 Squadron, the Dam Busters, crews trained for jobs other bomber units never saw. Their quarry that spring was the Bielefeld Viaduct, a stone monument to Prussian stubbornness and Allied frustration. Built between 1845 and 1847, the bridge spanned the Johannesbach Valley with 23 giant arches, each about 50 feet tall. It had been meant to last generations, and by March 1945 it had proven it, shrugging off wave after wave of attacks. 54 raids had battered the surrounding countryside. The RAF and American heavy bombers had poured in more than 3,500 tons of conventional explosives. Fields around Bielefeld were lunar with craters. Tracks had been smashed and patched again and again. Yet the viaduct's massive stone arches still carried trains, stubborn, unbroken, moving men and materiel to Germany's shrinking front. This was the kind of target that carpet bombing simply couldn't fix. A point of ancient, efficient engineering that resisted blows spread across wide areas. What was needed wasn't volume. It was one concentrated, penetrating punch right where the structure was weakest. On March 13th, orders came down. 1 Lancaster, 1 Grand Slam, 1 aim point. Squadron leader Calder would take the modified Lancaster fitted to carry Wallis's earthquake bomb. The plan looked risky on paper. The aircraft would fly alone, no stream of bombers, minimal fighter escort, and climb well above normal bombing height to gain the speed the Grand Slam needed. The crew would use an advanced bomb sight and drop visually in daylight. Every part of this profile broke RAF routine, but routine had already failed Bielefeld dozens of times. March 14th dawned clear over Lincolnshire. Rare fortune for a daylight precision run. Calder's Lancaster struggled into the air at 09:45, the airframe sagging under the 22,000-pound payload. The climb to operational height took 45 long minutes, 4 Merlins howling at full throttle. By the time the bomber crossed into German skies, it was an isolated, lumbering machine, too heavy to twist and turn if fighters appeared. Fortunately for them, By March 1945, the Luftwaffe's punch had nearly vanished. Fuel shortages and losses kept most interceptors on the ground. At 12:47, the viaduct came into view. Calder steadied the Lancaster at 20,000 feet, while the bomb aimer took careful readings, and the crew held their breath. This was no blind drop from the dark, and it was a single, deliberate strike aimed to do what 54 raids could not: hit one stone, one foundation, and bring down the bridge from beneath. The Grand Slam hung exposed beneath the Lancaster's belly, its tail fins like a dark promise against the sky. At 12:49, the release lever clicked. The bomb dropped, and for a heartbeat, nothing dramatic appeared to happen. Then it was gone, falling so clean and fast it seemed to vanish into the air. From 20,000 feet, the descent took roughly 40 seconds. Calder shoved the Lancaster into a sharp bank to clear the impact zone. Every hand on board braced for the unknown. No one had ever put a weapon like this onto a bridge before. The Grand Slam struck the ground about 30 feet from the viaduct's base and drove down through earth and rock before it detonated. The blast was not a cinematic fireball. It was a subterranean rupture, a throbbing seismic pulse sent through the soil. Two of the stone arches gave way instantly, as their foundations were shattered from beneath. A run of roughly 200 feet of the viaduct collapsed into the valley. What unfolded beneath Bielefeld that second explains why the Grand Slam succeeded where tons of ordinary bombs had failed. Surface explosions throw most of their energy into the air. A flashy blast, heat, and flying fragments, but only a sliver of that force goes into the ground. Against massive, well-built stonework, surface blasts chip and crack but rarely bring the whole thing down. The Grand Slam worked on different physics. From the moment it left the bomb bay, gravity and aerodynamics turned the weapon into a high-speed penetrator. Its long teardrop profile and hardened steel nose were built to slice through air and soil, not to burst on contact. At impact, the bomb was approaching roughly 750 miles per hour, nearly transonic. And with 22,000 pounds behind it, the kinetic energy was enormous, measured in the millions of foot-pounds. The forged one-piece steel casing deformed slightly on impact but held together, behaving like a drilling projectile and forcing its way deep into ground layers before the fuse timed the charge. When that buried charge finally detonated, the shock traveled outward through rock and foundation like an artificial earthquake. The force heaved the earth, ruptured footings, and made the arches collapse from below. Precisely the effect Barnes Wallis had imagined. The Grand Slam didn't stop at the surface. Its momentum drove it down through layers of earth that ordinary bombs simply couldn't breach. Post-war studies of soil mechanics showed these weapons typically punched between about 90 and 130 feet below ground before coming to rest. At Bielefeld, the surveys later estimated the slam reached roughly 95 feet before its fuse fired. When roughly 9,135 pounds of Torpex detonated nearly 100 feet underground, the result was not a blazing skyburst but a violent translation of explosive force into the ground itself. Air absorbs and diffuses blast. Packed soil and rock do not. They carry seismic energy with ruthless efficiency. The buried explosion sent out a rolling ground shock on the surface while compression waves tore through the subsurface, the sort of concentrated disturbance seismologists would compare to a localized quake of roughly magnitude 4.0 to 4.5. That seismic pulse was the killer. The viaduct's stone arches, engineered in the 1840s to bear heavy vertical loads, locomotives, freight, steady pressure, had never been built to withstand sudden vertical accelerations from below. When the shock struck the footings, the earth first thrust upward and then dropped away. Different parts of the arch moved at different speeds. Mortar joints that had held for a century cracked open. The carefully balanced geometry that made those arches so durable under normal stresses became a liability when their foundations started to shift independently. The Grand Slam also created a subterranean cavity. The intense heat and pressure near the blast center vaporized material within roughly a 40-foot radius, leaving a void. As the shock passed, that void partially collapsed and the ground around it slumped, producing secondary shifts for seconds after the main detonation. Foundations that survived the initial pulse suddenly found themselves unsupported, hanging over newly formed hollows. Witnesses described the viaduct's end not as a single, Explosion so much as a terrible sagging and then collapse, as if the earth, under the stones, had briefly turned to liquid. This is the heart of the contrast between British and American heavy bombing philosophies. It wasn't merely a numbers game. When you compare 5 B-17s delivering dispersed loads to one Lancaster dropping a grand slam, you're not just tallying pounds of metal. You're comparing coverage versus concentration, surface disruption versus buried kinetic force. The grand slam's power lay in its ability to change the medium that received the blast, to turn explosive energy into a directed subterranean assault that conventional aerial bombing could not replicate. You're not just comparing two bombers here. You're comparing two entire philosophies of destruction, two contrasting answers to the same question. What is strategic bombing really meant to achieve? 5 B-17s on a typical 1945 run might haul a combined 20,000 to 25,000 pounds of ordnance, about the same total weight as a single grand slam. But those American bombs were scattered across 5 aircraft, spread hundreds of feet apart in the air, each bombardier releasing independently through his Norden sight. At 25,000 feet, precision was more wish than science. Even in perfect conditions, the circular error probable, the radius inside which half the bombs would land, averaged around 1,000 feet. In practice, those 5 B-17s were saturating a quarter-mile circle with explosions and hoping the actual target sat somewhere inside it. The effect of that distribution mattered. Those 20,000 pounds weren't all massive warheads. They were a mix of 500 and 1,000-pound general-purpose bombs, maybe with a few incendiaries thrown in depending on the mission. Each weapon detonated on or near the surface, gouging craters and shredding everything above ground. Against soft targets, factories, depots, rail yards, wooden towns, that kind of wide saturation worked brilliantly. You erase the map. But against hardened points like submarine pens, reinforced bunkers, or stone viaducts, it was almost useless. You got chipped concrete, not collapse. It was the difference between throwing a handful of gravel at a wall and driving a sledgehammer into its cornerstone. That sledgehammer was the Lancaster carrying a single grand slam. One aircraft, one bomb, one aim point. By 1945, 617 Squadron's elite crews were hitting within 300 feet of their targets from 20,000 feet. Astonishing accuracy for the era, and all 22,000 pounds of explosive force struck in one place, penetrating deep below the surface where ordinary bombs never reached. The devastation came not from the blast above but from the shockwave below, collapsing foundations, liquefying soil, and tearing structures apart from within. The philosophies diverged just as sharply in their approach to risk. 5 B-17s meant 50 men. Lose one aircraft, 10 men die, but the other 4 complete the job. It was a system that distributed danger and relied on numbers, betting that 100 bombers could overwhelm the sky through sheer presence. The British approach with the Grand Slam reversed that equation. 1 Lancaster, 7 crewmen, 1 bomb. All or nothing. If flak or a mechanical failure took that single aircraft down, the entire mission, and one of the most complex weapons ever built, was gone. In essence, the Americans wagered on quantity and endurance. The British, with Wallis's Grand Slam, wagered everything on precision and singular force, the belief that one perfectly delivered blow could achieve what thousands of smaller strikes could not. By March 1945, the sky had changed. German air defenses were a shadow of their former strength, and that made lone aircraft precision strikes survivable. The RAF, willing to accept greater risk to crews, embraced the payoff. A single Lancaster with a Grand Slam could do what whole wings of bombers could not. Money matters too. A Grand Slam cost roughly $4,000 to build in 1945, a serious sum then, worth months of wages for a skilled worker. But stack that against the alternative. Dozens of raids, hundreds of sorties, huge fuel and crew costs, and the steady toll of men and machines thrown at a target that simply would not fall. Bielefeld had survived 54 attacks. How many aircraft? How many tons of explosives? How many lives had been spent chipping at that stone before one Grand Slam finished the job? When you count operational expense and human cost, The earthquake bomb often proved the smarter investment, one precise strike where many raids had failed. The Grand Slam's combat life was short. Between March and May 1945, only 41 were dropped. Still, their impact outlived their use. After the war, Allied teams cataloged damage across captured territory, and the lessons were clear. For some hardened targets, depth mattered more than sheer surface blast. That idea didn't vanish with the Lancasters. It shaped the weapons of the Cold War and beyond. U.S. military engineers, initially skeptical of super-heavy bombs, took notice almost immediately. By 1946, American labs were studying the Grand Slam's design and the post-raid reports. The result? Projects like the T-12 Cloudmaker, an enormous American penetrator that pushed the earthquake concept further, though it never saw combat. The principle, however, stuck. Specialized weapons for specialized hardened targets became part of doctrine. When NATO planners faced deeply buried Soviet command centers and missile silos, roofs of 20 to 30 feet of reinforced concrete often under more earth, they understood conventional iron bombs were futile. The solution traced straight back to Barnes Wallis: hardened casings, delayed fuses, and the physics of penetration. Weapons like the BLU-109 bunker buster of the 1980s borrowed that same rulebook. Hit hard, hit deep, detonate under the protection. Modern precision-guided munitions simply completed the arc, combining deep penetration design with guidance so that a single, accurately placed strike could do in minutes what mass bombing might never achieve. The story didn't end in 1945. It echoed forward through decades of weapons development. In 1991, engineers rushed the GBU-28 into service to punch through Iraqi command bunkers. At about 5,000 pounds, it could bite through roughly 20 feet of concrete or 100 feet of soil. 2 decades later came the GBU-57, the massive ordnance penetrator, tipping the scales at about 30,000 pounds and built to reach facilities no earlier conventional bomb could touch. Both trace their DNA back to Barnes Wallis, heavy, hard, and accurate, designed to make the ground itself betray what sat above it. That same lesson influenced post-war aircraft thinking as well. Britain's V-bombers, the Avro Vulcan among them, carried fewer guns and far more emphasis on what they could haul. The Vulcan sacrificed defensive armament for flexibility and payload, gravity nuclear bombs, large conventional stores, and later standoff missiles. That willingness to trade armor for carrying capacity was a direct heir to the Lancasters' philosophy. But the deepest legacy was doctrinal. The Lancaster and the Grand Slam proved a stubborn truth. Some problems don't yield to volume. They demand the right tool. Modern air forces now keep specialized munitions for specialized tasks. Bunker busters for hardened facilities, thermobarics for enclosed complexes, penetration warheads for tunnel networks. One correctly chosen weapon can accomplish what 1,000 blunt instruments never will. Today, the Lancasters sit in museums. Their bulged bomb bays a reminder of an era when designers dared to rethink the problem itself, rather than simply add more bombs. Visitors gape at the cavern that once swallowed ordnance measured in tons, not pounds. And the lesson those machines taught remains current. Design the weapon to fit the target, not the other way around. The Lancaster could deliver what 5 B-17s could not, because it was built to solve a different problem. In war, that difference is everything. That difference is everything.